Hey everyone, my name is Ethan Jones, and this is my final lab here at Georgia Tech for Physics 2211. It's Lab 5, the world's largest rope swing. So in this video, we'll cover the video or the experiment, the code, the energy principle, and using a spring to represent the rope. So the purpose of this lab was to test if the energy principle is conserved and explain why a rope is like a spring. So as a preview of the results, the energy principle is conserved, and treating the rope as a spring does work in the code. So, for the models, the initial conditions, the system was everything, their surroundings were nothing. The mass was 70 kilograms because that's the average mass of a person. The initial position was negative 45.72 meters in the x position and 0 for the rest, because this is the length of the rope from the video, and this will result in an arc. The initial velocity was 0 meters per second, and the spring constant K was 11,000 Newton meters, which I found was the average constant for climbing ropes. And then LO is 45.72 because this is the length of the rope from the video, which they tell us. And that's meters, by the way. For the models, Newton's second law. I use Newton's second law, which is force equals mass times acceleration, and F net equals all the forces added up. I use this because we were measuring motion, which requires an understanding of the net force. And I said the force of gravity equals negative mass times the constant G, and the force of the spring equals negative constant K times S, which is the difference between L and L naught, times L hat. I also use the energy principle, which is delta E equals work, which equals delta K plus delta potential. So I use this to measure the changes of energy in the system. So I use the delta kinetic energy formula, the delta gravitational potential formula, and the delta gravitational spring formula. And I also use the velocity update formula and the position update formula. So this is the video that I looked at. So as you can see, it's a giant rope swing. Very cool. Unfortunately, because the camera moves and because there's so many cuts, I couldn't quite track this data, but I try to make my code look close to it. So I have all the visuals here in the code, and then this is the part that I actually plugged in numbers for. So I put the mass in, all the initial conditions, the position, velocity, all that, the constant K, L naught. And then I found L by subtracting the position of the person from the spring, and then I found L hat and S, and then I found all the energies, kinetic energy, gravitational potential, gravitational spring, and then I found total energy by adding all these up. And then I created a loop here. So I found the force of gravity, the force of the spring, and then I found F net by adding these together. Now I've used the position or the velocity update formula and the position update formulas to update the position and all that. And then I updated the spring itself, and then I finally calculated the energy changes. So I found the new K and subtracted the K final from K initial to get delta K. And then I did the same thing with the potential energies. And then I found total E equals kinetic plus potential gravitational plus potential spring, and then delta E equals all the changes in these. So my code made a model that looked like this. So it started up here and swung in this arc and just went back and forth. Unfortunately, I could not get the video in this presentation. I tried. So for the energy principle, as you can see in this graph over here that the code created, the energy principle does stand true. There's never a change in the total energy of the system. As you can see by this yellow line, it's always on 0. And in real life, there would be drag, so there would actually be a negative change in total energy. So delta E would probably be like down here. So rope as a spring. So rope can be modeled as a parallel chain of atom and spring-like bonds, as you can see over here. This can be thought of as one large spring with a large constant K. So for possible sources of error, the code did not account for drag, so this will vary from real-world observations. The code could also not model a drop before the rope was stretched. The mass of the person and the spring constant were estimates that I found online. So in conclusion, the energy principle stands true as the total energy of the system doesn't change. We can use a spring to model a rope swing to predict real motion and extreme scenarios like this. All right, thank you for watching and have a good day.